Hello everyone. Welcome to our channel. In our previous video, we talked the ultimate math powers, where we have dived deep into the mysterious world of exponents. Both real and imaginary. Have you ever seen something like 0 to the power of 0? And thought, wait, what? Is it 0? Is it 1? Or something undefined? Today, we're going to explore this tiny but powerful mystery, 0 to the power of 0. From the exponents laws we know, any number to the power of 0 equals 1. On the other hand, based on the arithmetic rule, multiplying n numbers zeros equals 0. That is, 0 to the power of any number n equals 0. Thus, if every number to the power of 0 equals 1, then it makes sense that 0 to the power of 0 should equal 1, too. Right? However, it seems both rules talked above collide obviously. What happens? Now we come to explore the limits of x to the power of x and focus on non-negative value of x. Let's try some examples. If x is 0.5, we got the result equals 0.707. If x is 0.1, we have the results of 0.79. If x is 0.07, we got 0.95. When x gets smaller and smaller approaching 0, the limits of x to the power of x is getting closer to 1. Let's go back to 1752, when the famous mathematician Leonhard Euler declared that 0 to the power of 0 equals 1. Euler and others found this definition convenient. It made many formulas and patterns work beautifully. In 1814, Pfaff used the squeeze theorem argument to prove that the number x to the power of x goes to 1 as x approaches to 0 from the positive side. Now we graph the negative number a to the power of any number x. We notice that there is a problem. If we look closely as the number approaches 0, it behaves strangely. For negative exponents x, the result shoots to infinity. For positive exponents x, the results drops to 0. And as x is equal to 0, suddenly, the results is 1? That is a huge jump from infinity to 0. Next, let us examine in detail what is going on mathematically step by step illustrated in a video. Actually, in the 1800s, Cauchy showed that if both the base and the exponent approach 0, the result could be anything, 0, 1, or even infinity, depending on how you approach it. So in calculus, 0 to the power of 0 is indeterminate. It is also called an indeterminate form. Depending on how both numbers approach 0, the result can be 0, infinity, or 1. Here we present systematically the timeline in the history of 0 to the 0 power, starting from Euler in 1752, to Mascheroni in 1787, to Cauchy in 1821, Libri in 1830s, to modern mathematics. Now let us watch a video. From this video, we can summarize. Algebra says, define 0 to the 0 power as 1 for convenience. Calculus says, careful. It depends on the limit. That is why mathematicians say, this value is sometimes 1, sometimes undefined, but always interesting. Next, let us see some examples. Defining 0 to the 0 power as keeps many mathematical formulas consistent. Polynomials, power series, algebraic evaluation, and calculus, all ensuring formulas and limits work smoothly at x equal to 0. Okay, watching the video to see what it presents in detail. Many widely used formulas, involving natural number exponents, require 0 to the 0 power to be defined as 1. For example, the presented three interpretations of the number b to the 0 power make just as much sense for b equal to 0 as they do for positive integers b. As for continuous exponents, the value of 0 to the 0 power is indeterminate due to the limit's behavior. For complex exponents, the value of 0 to the 0 power, however, is not defined at all. In programming and software, most systems define the value of 0 to the 0 power equal to 1 for convenience, though some leave it undefined or treat it as an error. Watching the following video for details. What do you think that 0 to the power of 0 should be? Leave a comment below. And don't forget to like, share, and subscribe for more fun math mysteries.